Hi, how's it going? Andrew here from Get Into Game Dev. I upgraded my camera, not my room though. Same room. Welcome to my series on real-time ray tracing in Python. In this series, I'm going to be going through the basics of compute shaders. Basically, it's compute shaders. I couldn't find a lot of info on using compute shaders, though what I did find was pretty good. So, just want to make this series. To start with, all the code is available as usual with like a start point and a finish point, so you can jump in and see what we did, see what I did. But this is what we basically have. So we're starting with completely nothing. We have this ray tracing program that creates an app. The app has the usual stuff. So we set up screen height, screen width, request OpenGL version 4.3. 4.3 is needed for compute shaders. That's just how it is. Then, we set up our core profile, just the usual Pygame setup, really bare bones. We have a graphics engine, which handles the rendering, and that is called every frame during the main loop. But onto the meat and bones of it, which is the graphics engine. So again, we're basically starting from scratch. So what we do is we have this graphics engine, takes a screen width and screen height. It has a quadrilateral, so a rectangle, which covers the screen. And then it renders to a texture, and the texture is bound to the screen, and that, it's a standard sort of custom frame buffer sort of setup. So we're drawing a texture over the whole screen. That's what this create shader does. If we like, we could jump into this. Okay, so we just take a position and a texture, pass that through. This is just basically rendering 101. And then for the fragment, we sample from a frame buffer. So in other words, we're just taking the texture that we have drawn to, and we are sampling from that and sticking that on the screen. This is a standard kind of shader toy kind of setup. Like whatever we put in that texture, it'll be on the screen. Okay, so then we have the ray tracer shader. And for that, we have this compute shader program, which is pretty similar to the regular shader program. Okay, so for the regular shader program, we had a vertex shader and a fragment shader. We compiled those and we linked them together into a program. For the compute shader, we read it, we compile that to a shader, and we pass in this GL compute shader flag, and that creates a compute shader for us. And that's our program. Awesome. Okay. Then we have a quad, and the quad basically is going to just cover the whole screen and with the whole texture. So we have texture coordinates and positions, and this is just running from left to right, top to bottom, covering the whole screen with our texture. Okay, cool. Then we have a color buffer. Now this is where things get a little interesting. So we make a texture, we start working on it, and it doesn't matter which address mode we use here. It could be clamp to edge, clamp to border, any of that is fine. I just like to use repeat. But this is super important. It needs to be nearest filtering. And the reason for that is that images are treated slightly differently. So here's a preview. When we go to the fragment, when we pass in our color buffer as a texture, that's treated as a sampler 2D. That is an image plus a protocol for getting into the image and accessing pixels. We could be doing linear filtering, nearest filtering, quadratic filtering, whatever we want to do, okay? But when we access the image from a compute shader, that is treated as an image 2D, not a sampler 2D. In other words, that is just the image data. And the only way we can access that image data is indexing into it with integers, because we are getting the actual pixels. We do not have any sampling operations set up. There's no linear filtering or anything. So for that reason, it's super important. It needs to be nearest filtering. So what I'm doing is I've created this texture, I've configured it, and now I send it in, and I declare it as an RGBA32F texture. What that means is a 32-bit float is used for each of these components. Okay, so we're using a little bit more space, but yeah, but that is okay. We're just declaring it with no data at the moment. That data will be filled in later. So far, so good. So now let's go and render the scene. What are we doing? To start with, pretty much not much, okay? So we use our Raytracer shader, that's our compute shader. We set up texture 0, it's a good practice, and then we need to bind our image texture. So we bind the self color buffer to index number 0, and then these arguments here are like whether we're using image layers, whether we're using bitmap levels, we're not doing any of that. Okay, so we just set this to 0, false, 0. We need to bind it as write only. Okay, so it's a write only mode. Super important. And we declare the type. Okay, then we call dispatch compute. So a ray tracer works with a massive number of jobs. Okay, and each job is coloring each pixel of the screen. So when we call dispatch compute, the arguments that we pass in are the number of groups for X, number of groups for Y, number of groups for Z. Okay, so by putting in the screen width and the screen height, we are saying for every X pixel, every X coordinate, every Y coordinate, ray trace. Do a ray tracing job, dispatch a ray tracing job. And the graphics card will do the best to parallelize that the best it can. It could potentially be using, you know, one core per pixel on the screen. That's insane, but it tries to do something like that. And then Z we're setting to 1, and that's equivalent to saying don't worry about Z. Like think about it like we have a flat texture, so its Z coordinate is 1, and we're just writing every pixel on it. Okay, so that gets sent off and it does its work, and it could potentially still be doing its work. So we need to synchronize this and wait to make sure that we finish the work before we take that texture and draw it on the screen. Okay, so what we do is we call our memory barrier on image access. Okay, so everything else can go along until we reach the point where we start sampling from the texture, and then this memory barrier, it will wait on that if that work is still being done. But otherwise, yeah, it's just the usual stuff. So then after we've done that, we draw the screen. That is, we switch to our regular like texture on the screen shader. We bind to the regular frame buffer. This is just best practice. We load in the color buffer as a read texture, and then we go for it. We bind the quad and we draw it. Okay, so I probably took longer than I had to go through that detail, but it's important, I guess. So let's just run this right now. And everything is yellow. That's good. It's working as we expected, because but earlier I set this up and I said, hey, we've got a pixel and we're going to make it yellow. So let me just make it red right now and run it again. That's good. Okay, so what's happening is our ray tracer is setting the pixel to red and then writing that to the texture for the color buffer, and then the regular shader is drawing that color buffer on the screen. So let's go into this ray tracer. So we're using OpenGL 4.3. Again, that's a minimum requirement in order to use compute shaders. And then we have this layout, the data that's coming in. Now, that is basically saying how many jobs are being done by this shader. It's just doing one job in the X, one job in the Y. In other words, one pixel. Okay. And then we declare that we are going to write out to this image output texture. That's binding number 0. Okay, in order to get the pixel coordinates, we can do that by using this global invocation ID and getting the XY coordinates of that. That's an IVEC2, an integer vector 2. It also has a Z coordinate, but we're not worrying about Z for this. So, I mean, yeah, this is the most simple thing we can do. Run this again. And yeah, we're writing red data, we're reading red data, it's all red. You could play around, change it, make it different colors. But that's not what I want to do. Just to test that our ray tracing stuff is working, let's create a ray tracer. So to test that our ray tracer is working, we're going to make a really simple scene. If our pen can work. So we're going to set this up with the x-axis, z, and y. And our camera is going to be bang at the origin. It's going to have a bunch of really important directions. We're going to have a forward direction, which is going to be in the positive x direction. If we orient ourselves here, then we can say our up direction is in the positive z, and then the right direction will be in the negative y-axis. That seems a little weird, but actually, no. It is a little weird looking at it now. Let's actually, I don't know. We might adjust this later. So we'll put the right in the positive y. It's fine. Okay, now what we'll do is we'll have a sphere which is centered somewhere along the x-axis because we're looking this way. And we're basically going to be looking at the sphere. So what we're going to do is, given our pixel, we're going to have some position, some combination of the forwards plus the right and the up. So we can kind of visualize this as like a plane which sits in front of the camera. Taking a combination of up and right plus the forward will give us a bunch of pixel positions in this plane. What we want to do is we want to set up a ray which is originating at the camera's position, going through each of these pixels. Then we want to test whether that ray hits our sphere somewhere. So it's a little messy here, but let me just I'll put A for the ray's origin, dir for the direction of the ray, and then we'll put this will be P, this will be the point where the ray hits the sphere, and we'll put B here for the center of the sphere, and there's some float radius there. So we have a bunch of things. Based on the ray, the position of the point will be the origin point plus some parameter times the ray's direction. Based on the sphere, well, the sphere is the set of all points which are radius r from this center. So what we've got is the magnitude of the point P away from the center. The square of the magnitude is equal to the radius squared. Now the magnitude itself is equal to the radius, but doing this in squares is a lot easier. So what we can do now is we can take this expression for the position of the point along the ray, plug it into the expression for the condition on the sphere, and that gives us an equation. Okay, now we've got this magnitude squared, and magnitude squared is equal to the dot product of a vector with itself. So what I'm going to be doing is using the inner product notation. So when I put these angle brackets, I just mean a dot product. I'm going to go lump the A and the minus B together. Okay, so what this is saying is the dot product of this vector with itself, that expression is equal to its magnitude squared, is equal to r squared. And now what we're going to do is basically rearrange this and use some properties of dot products, linear operators, to get it into a different expression. So first of all, we will expand basically the left side. And then expand the right bit there. Okay, because t is a float value, not a vector, scalar value, we can pull that out the front as a multiplier. So we've done about half the work here. Now we need to expand the right-hand side. And basically what it comes down to is we have this expression here. So the dot product is symmetric, so we can change the order around here. That's fine. Commutative, I mean. And what we get here is our goal is to solve for t. And we've pretty much got a quadratic equation with respect to t. So I'll just rearrange this. That should be a minus there. Okay, so there we have it. We have pretty much a quadratic equation. Analyzing this, we can see we have our coefficients a, b, and c that we're used to. And we know that this has an expression, this has a solution of the form t is equal to minus b plus or minus that expression there over 2a. And furthermore, this is solvable if the discriminant, that's this expression here, is bigger than or equal to 0. I'm going to go with bigger than 0 in this case. Exactly equal to 0 would be right on the rim of the sphere, and that doesn't matter at all. Okay, cool. So that's it. This is the expression for t. Once we get t, we can plug it back into our ray equation. And point is origin plus t times the direction, and that gives us the position in 3D space where the point has hit the ray. Anyway, that'll be it for this. So for now, I'm going to declare a lot of this, just hard code it. That's perfectly fine. Okay, cool. So we've declared a bunch of structs. The thing is, with this GPU computing, shader programming in general, it's kind of a bit simpler than regular programming. So we don't have pointers or anything. We have to pass around data things by themselves, but they're not. It's generally not too bad. So anyway, we've declared these structures. Now what we're going to do is in our shader, we will get a few other things. Okay, so for one thing, we want to know how far to the left or right our pixel is, and we don't just want the integer for that, we want a float. Okay, so we're going to do kind of like normalized device coordinates. So -1 on the x will be the left, and all of that. So we're going to need the size of the screen. So there's this function called image size, which returns an IVEC2, which is the dimensions, length and width. Okay. Okay, so what we've basically got here is this will just be varying between a positive number and a small number, negative number, and we normalize that by dividing by the screen size in both dimensions. and we rename that because that would be crazy. Why can I not type? Hey, side note, why can I not type ever? I don't know. Okay, so we've got that. Now what we need is camera. Okay, so we're just going to set the camera up at the origin. Its forwards direction is going to be just looking along the positive x-axis. And its right direction is going to be the positive y-axis. Okay, cool. Next object we're going to worry about is a sphere. So we're going to put a sphere in our scene. So it's just a bit F in front of us on the positive x-axis. And for the radius, we'll make that just 1. And for the color, I don't know, doesn't matter. What did I do here in my example? Let's go 1 in the red, 0.3 in the green, and 0.7 in the blue. So it's going to be a kind of a pinky color. Okay, so we take the camera's forwards direction plus the horizontal coefficient times the camera's right direction plus vertical coefficient times the camera's up direction. Cool, awesome. So that is set up. Next thing we need to do is we've got everything good to go. We're just going to trace and see if we hit the ray. We're not going to worry about getting the position on the ray or the normal on the ray or anything like that. Those things aren't hard to do, but we're just going to test whether the ray going through our certain screen coordinate can hit the sphere. So in order to do that, we'll basically set this up as if we were going to solve the quadratic equation. So we'll get the A, B, C coefficients. And that's not door, that's dot. Cool, cool, cool. All right. So then we have that discriminant. Which is, what is it? It's b squared minus 4ac. Okay, so the test is if that discriminant is bigger than 0, then color the ray, or color the pixel. So in this case, pixel is increased by the color of the sphere. Okay. Side note, putting a conditional statement like an if does not speed the shader up one single bit. In order for the shader to parallelize, horrible word by the way, parallelize the workload as much as possible, it needs to make sure that exactly the same code is running on every single thread, every single core, and all of that, every instance of this. And in order to do that, it needs to create a shader where both branches of the if statement are evaluated. Then it selects after the fact. So there are some things, yeah, this is one of them. Putting an if statement in a shader will not speed it up at all. But fingers crossed this should be working. So we run this right now. And of course it's not. So what's the issue? Okay, that's funny. Oh yeah, of course. What have I done? What have I done again? 51. This is just me typing too fast. Yeah. There we go, forgot the bracket. There we go, here's a beautiful sphere, but we got a problem. Of course, a sphere is supposed to have equal radius in both directions. What's gone wrong? Basically, because our width of our screen is larger than our height, we should be normalizing based on the larger or the smaller of those two coordinates, right? Because our width is larger than our height, we should not be seeing up as much as we're seeing across. Do you know what I mean? So normalized device coordinates, both x and y, would range between -1 and +1. But for these coordinates, they're more like projection or screen coordinates. So what I'm going to do is I'm just going to normalize based on x because that's a larger dimension, and that more or less solves it. So we have a sphere. Now, we don't have lighting, we don't have multiple spheres, but this is pretty cool. We got a compute shader working. Compute shaders, they kind of, I don't know, they're a big thing. They're a big deal. And if we can learn to use them properly, there are heaps of things we can do. We've just taken our first steps right now. I'm super excited. I hope you're excited. And I'll see you in the next video where we continue this further. All right, bye.